Now what I'd like to do, now that we've covered modular arithmetic, is I'd like to move on and like to introduce the definition of an equivalence relation, and then we'll follow this up with some examples. So an equivalence relation tilde on a set S is an operation that satisfies three properties. First of all, we'd like for this equivalence relation to be reflexive, meaning that for every element of the set, we would like A to be related to itself under tilde. The next property that we'd like is we'd like tilde to be what's called symmetric, which means that if we know that A is related to B, then B is also related to A. So we can interchange the roles of A and B, and we still want this relation to hold true. And the last property is what we call the transitive property, which is if A is related to B and B is related to C, then we would like it to be true that A is related to C. Now, the members of a set that are similar under this equivalence relation are called an equivalence class. So I introduced that symbol, which is that squiggle, which is called tilde, but it is also the case that we sometimes say that two elements are similar, they're related. Those are words that we throw around with that tilde as well. And in fact, some books don't use a tilde for an equivalence relation, they use a capital R for related, saying two elements of a set are kind of similar or related or thought of as the same somehow. Let's start out with some examples of equivalence relations and also some non-examples. So each of the following is an equivalence relation on a set. So here's an example. If S is a non-empty set of integers, and tilde is actually the concept of being equivalent modulo a particular number, non-zero integer n, then this forms an equivalence relation on the set of all elements that have the same remainder when you divide by that non-zero integer n will break the set up into an equivalence relation. Very fitting, if S is a set of triangles and we say that two triangles in the set S are similar, if they are similar figures, that is, they're sort of scalar multiples of one another, then this will partition the set S into an equivalence relation. And last but not least, well, the last example that we're going to present here today is that if S is a set of fractions, then we can consider two fractions to be the same. They may not actually be the same, but if they denote equivalent fractions, then we'll call them the same inside the set. So for example, if S was the set that had 0, comma, 1 over 1, comma 2 over 2, then 0 would be similar to itself. It would be its own little equivalence class, and 1 over 1 and 2 over 2 are equivalent fractions. They're not literally the same as fractions, but they are equivalent. Now, on the other hand, let's give some examples of things that are not equivalence relations. If S is a set of numbers, and we let tilde be the relation that we're very familiar with, which is less than or even greater than, then this is not going to be an equivalence relation on the set of numbers, since this is not reflexive. It's not symmetric either, but in particular a number is not less than itself, so you're going to fail to be reflexive, and if you have a number, one number that's strictly less than another number, then we don't have symmetry either. You can't switch it around and have the larger number be less than the smaller number in addition to being greater than it. If S is a set of sets, and you use tilde to denote the subset relation, then it is true that this will be reflexive and transitive. Any set is a subset of itself, and if A is a subset of B and B is a subset of C, then A is a subset of C. So you have the reflexive property and the transitive property with the relation subset, but you don't have symmetry unless you have identical sets. So if you had one set that was a proper subset of another, then subset would not happen to form an equivalence relation. And just as a less mathematical example, let's suppose that S is a set of people, and we want to define a relation on these people, and the relation is, are these two people related, as in do they share sort of DNA better than like 52nd cousins or whatever the fact is, but let's say that A is related to B if two people are related. Well, a person is, this will be reflexive and symmetric, but not necessarily transitive. So you could think of a person as being related to themselves, so this would satisfy a reflexive property. If I am related to you, then you are definitely related to me, but it's the transitivity that's going to fail. So for example, if I have a cousin, then the cousin of my cousin is not necessarily my cousin. It depends on who their mother and father is. And so this relationship need not be transitive, and so the concept of two people being literally related is not necessarily an equivalence relation. I should say that in the definition of an equivalence relation, we had three properties: reflexive, symmetric, and transitive. When you're trying to prove that something is or is not an equivalence relation, it's often the transitivity that is the hardest. And if you're given a relation and asked, is it an equivalence relation or not, it's more often than not the case that this relation fails to be transitive. As you can see here, you can build examples of relations that are not symmetric or not reflexive, but more often than not what you're going to fail is the transitivity requirement, so that's often a good place to look if you're trying to double check to see if something is an equivalence relation or not. Now, as with all things, if you're going to prove that something is an equivalence relation, then what you want to do for this type of proof is use the definition. So if you have a relation and you want to show that it's an equivalence relation, you have to show three things. You have to show the relation is reflexive, you have to show that it's symmetric, and you have to show that it's transitive. If you're trying to show that something is not an equivalence relation, all you need to do is provide a counterexample. So those types of proofs tend to be shorter. What I'd like to do now is walk through formally and very accurately do all the work required to show that something is an equivalence relation. So let's suppose that S is the set of integers, and let's take two elements of the set and define them to be related. Say A is related to B if you take the quantity A plus 2B and you get something that's divisible by 3. Let's prove very formally that tilde is an equivalence relation. So as I said before, we have to show three things. Let's start by showing that the relation tilde that we've defined is reflexive, which means that we need to show that A is related to itself. That is, if I take A and add on 2 copies of A, then what I get needs to be divisible by 3. That will show that A is related to A and that our relation is reflexive. So what I need to do is look at A plus 2A, which is 3A. This is very clearly divisible by 3. It's 3 times something. And this is all we need to do to show the reflexive property. To show the symmetric property, what we need to do is suppose that A plus 2B is divisible by 3, and then we need to show that when I change the roles of A and B here, and I consider B plus 2A, I need to show that this is divisible by 3. So to do this, and to also do transitivity, I'm going to use some properties of being divisible by a particular number, which is if I take 2 multiples of 3 and add them together, or subtract them, then what I get is a multiple of 3. So here's what I'm going to take. I'm going to take B plus 2A, which is the number in question, and what I'm going to add on to that is A plus 2B, which I'm supposing is a multiple of 3. And when I do that, I have 3 copies of A and 3 copies of B. So the quantity B plus 2A plus A plus 2B is 3 times the quantity A plus B. Okay. 3 times the quantity A plus B is very clearly a multiple of 3, and by hypothesis, A plus 2B is a multiple of 3. It's divisible by 3. So when I take the difference of these two things, the quantity 3 times A plus B, and then I take and subtract off A plus 2B, what I'm left with is B plus 2A. That's the thing I wanted to know something about, and I've just argued that this is the difference of 2 multiples of 3. And so when I take 2 multiples of 3 and I subtract them, what I get is still a multiple of 3, and that's enough to show this symmetric property. A very similar argument is true for the transitive property, so let's take a look at it. What I need to do to show transitivity of this relation is I need to show that if I assume now 2 things, I assume that A plus 2B and B plus 2C are divisible by 3. That's what I get to assume. Then what I need to prove is that A plus 2C is divisible by 3. So I'm going to use the same logic as I did with the symmetry property. I'm going to find 2 different multiples of 3, and I'm going to show that A plus 2C is the difference of 2 multiples of 3. So here, let's take a look at A plus 2C, which is the thing, the number in question. Let's add on a multiple of 3 to that, which is 3B, very obviously a multiple of 3. And let's regroup all the terms that we have. Let's break up that copy of 3B. let's take 2 of those copies of b and add them to the a first, and then let's take that leftover copy of b and add it to the 2c. And then what I'm looking at is this quantity a plus 2b, which I'm assuming is divisible by 3, and b plus 2c, I'm also assuming that that's divisible by 3. And so what happens is a plus 2c plus 3b, which is equal to this thing over here on the right, is a multiple of 3. So a plus 2c plus 3b is a multiple of 3. 3b is obviously a multiple of 3. And so when I subtract them, what I'm left with is a plus 2c, and that thing that I'm left with, a plus 2c, must be divisible by 3.